Thank you so much, Roberto or Giorgio, or should I call you? I don't know. My work is about Boltzmann. The prize is about Beltrami, which actually I knew Beltrami, of course, mostly because of the beautiful pseudospheres. But when I did the exercise, I discovered two things. First, that Beltrami has done a lot of important contributions which are very modern. For instance, the Laplace-Beltrami operator is currently used to solve PDEs on manifolds, and this has many important applications in optimal shape design. The single eigenvalue decomposition, which is a basic tool in engineering and also in quantum computing, I recently figured out, also carries Beltrami contribution. And the Beltrami flows are very important for topological fluids. So, I mean, it looks like Beltrami really had work which is lasting the test of time. Boltzmann needs no introduction, but I didn't realize they are basically contemporaries, right? So the question came to me as to whether, by some chance, they might have crossed paths. And I looked into this possibility, and I discovered this beautiful paper. I don't know Riccardo Rosso, but that's a very nice paper. And where it informs us that Beltrami at some point was concerned with thermodynamics. Boltzmann, of course, laid down the microscopic foundation of thermodynamics. But he approached thermodynamics from the point of view of Truesdell, rational mechanics, namely using continuum field theory. And at some point in the abstract, as you can probably read, Beltrami occupied himself with kinetic theory, but he never mentioned probability. At that point, honestly, I gave up, because, as you know, Boltzmann physics is basically, the cornerstone of Boltzmann physics is probability. So I have to conclude that, unfortunately, the two contemporaries didn't really interact into any significant extent. Too bad, but that's it. So now the story, the lattice-Boltzmann story. Roberto, you stop me. I have a lot of material, but I mean, I can skip or stop anytime. So let's begin from the Jurassics. And the Jurassics, as I said, we are talking mid-80s. Some of you were not yet born. I was, and so was Massimo as well, by the way. And it began, it's a nice story, because there is a lot of serendipity.
So you started already for the title of the Jurassic because of your name.
Because of my name, yes, yes. And the question is which one I am in this picture. I don't know either. Well, how it all began, and that I think is useful for the young people and not so young people young people of any age in this room, because it really had to do with some very nonlinear aspect of life. Here comes one. So back then, I was coming back to Italy from Switzerland, and my PhD was not yet completed. And I was working in IBM, European Center of Scientific Engineering Computing, beautiful place. My boss was Roberto Benzi. Some of you know him. He had a group called Fluid Dynamics. And I was just beginning doing some work in that direction. At some point, the boss of Roberto, Piero Sguazzero, stepped into my office and said, Sauro, I have seen this paper. Why don't you take a look? This is Cellular Automata for Fluid Dynamics, 1986, okay? But the main reason was that I was supposed to learn how to program the IBM machine, which I did. Actually, those days I even did some assembler exercise. Yes, it was Piero. Okay, that's of course Massimo. No, I did, to the point that, in fact, I discovered even multi-spin code in Massimo, in Fortran. And so I, in fact, repeated this exercise. And of course, I could not find any Navier-Stokes solution, the simple reason being that on this lattice you cannot find fluid dynamics, because as you may notice, there are just 4 links. Okay? And with 4 links, some of you know, and for the others, this is the news, you cannot solve nonlinear fluid equations because you don't have enough rotational symmetry. In those days, I had no clue. I really didn't understand the point at all. And my reaction was, come on, give me a break. If I take enough grid points, I will retrieve fluid dynamics. And of course, I didn't. The reason being that, and please take a look at the date. This is PRL, 21 April 1986. Ahead of this paper, there was the real paper. And the real paper, as you can see, there is a change, minimal change of symmetry. You go from square to hexagons. And that's enough to deliver Navier-Stokes, which is interesting, right? Looks like a trivial thing. What is the difference between a square and an hexagon? Well, there is a small surplus of isotropy in this lattice, and this little surprise makes a completely different story. Here you can solve Navier-Stokes equation. This paper was a big one, and many big people got involved in those days. Stephen Wolfram, which is the mathematical Wolfram, that would be for the history science a quarrel, because Boltzmann claimed that it was his discovery, which was stopped by PRL in favor of, well, I shouldn't say that because it's too much, it's in the stream. But anyway, it was an interesting, there was a competition, let me put it this way, and the competition was very harsh because people felt it was a big deal, okay? Because in principle, with cellular automata, you could solve, I give you the bottom line, fluid dynamics in terms of Boolean algebra, so no round-off error. It was an exact way of computing fluids, and meaning that potentially, and it was very amenable to parallel computing, to the point that, and Feynman himself got involved in the latest stage of his life. At some point, yeah, on the Washington Post, there was an article saying this is so important that should be kept out of the Soviet hands. Don't forget, 1986, the Berlin Wall was still standing. And I would say it reminds a little bit of what is going back 2 days, where now we see this GPU, NVIDIA, with machine learning that between China and the US. But just to give you a sense of how important this was regarded at the time. Now, of course, I have no time to go into the details, but the bottom line is that you basically solve an equation which the left-hand side is basically the free streaming of particles, but the particles here are bits, 0, 1. So either you are sitting on the lattice side, 1, or you're not, or you're not. And there are 6 possible directions for the motion. So the left-hand side is just the motion from one lattice side to another, and the right-hand side is how these bits interact with each other. The key point, which is by no means trivial at all, is that these NIs are Boolean numbers, occupation number, like fermions in condensed matter. 0 and 1, nothing else. And the remarkable thing is that you can boil down an expression for the collision operator, which is compatible with the Boolean nature of the game. If you do the algebra, I just sketch it there. I don't know whether you can see a reaction Ij going to KL. The idea is that you should have a particle in state J, and particle in state J, and you should have no particle in state K and L because you have to fill these states. And if they are fermions and they are already occupied, there is no possible collision. By suitable combination of this type of operators, and there are operators for 2-body collisions, 3-body, up to 6-body, you construct this collision operator, and this operation takes only value -0 and +1, so it's compatible with the Boolean nature of the game. Big deal. Unfortunately, when you took a closer sight at this game, many important shortcomings were emerging, and that's how lattice Boltzmann was born. I will not really go into any detail, but essentially the way lattice Boltzmann was born is item number 1, because being Boolean numbers, you were swimming in the noise, okay? It took a lot of automata to generate a meaningful signal. And this is a very old picture, again, coming back to Roberto. This was my first PRL in 1988. And we ran, I still remember, it was a lot of fun. This was a huge calculation by then. We had big machine in those days, 8,000 by 8,000 automata. And I still remember how happy we were when we saw that the vortices were, not only were there, but they were moving quantitatively correct. This paper is not very well known, but I think it was really very early, one of the earliest demonstrations that the lattice gas would work. But look at the right side. This was Roberto, the very same days, using pseudospectral methods. And you can judge by yourself the difference. They were much more accurate and at least 3 orders of magnitude faster. So I remember the boss, the IBM boss, said, very nice work, guys, please switch to something else. Okay. But, and that's where nonlinearity of life came into play, I will skip Zanetti. He must be credited for realizing that if you want to do fluid dynamics, you don't need to do all these very costly collisions. You can directly move to the Boltzmann level and get rid of the noise beforehand. So the lattice Boltzmann is basically a noiseless lattice gas, or as Dan Frankel, which is a very important statistical physicist, he calls it pre-average lattice gas. That's what it is. You can formulate the theory, take this collision operator, which is exact, and average, take an ensemble average of the lattice gas collision, and do the crime. The crime is to replace the average, move the average inside, which you cannot do because it's nonlinear, and forget about it. That's exactly what Boltzmann does in continuum kinetic theory. It gets rid of many-body correlations. But many-body correlations are not needed to generate fluid dynamics from the microscopic level. And Gianluigi Zanetti, who unfortunately died in a very sad crashed in a plane crash. They realized it first, but they didn't pursue the lattice Boltzmann as a computational tool. Somehow they didn't see the fact that, yes, it is noiseless, but it can be used as an effective computation tool. And the big smile of Lady Luck to me came in 1988. Javier Jimenez was an IBM, part-time IBMer working in Madrid, and he sent me one of his students, Francisco Higuera. I don't know, Massimo, you were not, yeah. You were there. And Francisco came, and again, I really like to give the credit, because the lattice Boltzmann is not, certainly not a one-man story. It's really many people contributed. Francisco came to me, I don't know whether you can spot the figures over there. This was sort of museum of science. These were the graphics that Francisco came, brought along from Madrid, say, look, Sauro, stop doing the lattice gas. We have something better for you. Okay. I was still in my, German and Swiss PhD state of mind. I was doing my job with lattice gas. I wanted to get my job finished before doing something else. But happily enough, in the end, my Italian nature prevailed, and I switched to lattice Boltzmann. They realized that, again, this would be a long story, but essentially the idea is that in order to recover the Navier-Stokes equation, you don't need the molecular details. Okay? So the idea is that you formulate the collision operator in terms of relaxation. These are relaxation rates, if you want, of the actual Boltzmann distribution function, the probability for a particle to move along direction J, and J runs on the lattice, the same lattice I showed before, and you relax it to a local equilibrium, which depends on, in a very well-known way, on the density and velocity of the fluid. Okay? But the density and the velocity of the fluid can be computed. The density is just the sum of all the particles moving along all possible directions, and if you sum the momenta of the particle, okay, which are also known, you generate the velocity. So this is a self-consistent relaxation. The big deal is that you know this object, and all you have to do is a matrix vector product. Meaning that instead of having a complexity, B is the number of bits. In 3 dimensions, you would need 24 in those days. So on each point of the lattice, on each instant in time, you had to do 2 to the power 24 collision, 16 mega, which was a lot. Those days was unthinkable, and still today would be. A typical computation fluid dynamic code takes 1,000 operations per grid point per time step. Here we are talking 10 millions. Instead of 2 to 24, we have a matrix vector product, so we had 24 square, which was a totally different game. So this, to me, it was one of the most important breakthroughs in the subject. And when Francisco came and visited, we produced the first, actually, this is the very first lattice Boltzmann simulation ever published on a journal. And as you see, we basically quantified the intuition. this paper, was published in, I think in 89, and it is actually the way we validated the idea in a quantitative terms. And then came another breakthrough, and Roberto was my boss, and he came, having seen the results, said, look guys, since you now work with this formalism, and all you have to do is to recover the Navier-Stokes equation, why don't you design the collision matrix top-down? Looks like obvious, but you know, science is like that. Many obvious things are only obvious afterwards. And we did the job. You basically take the matrix, you know the symmetries that the matrix has to fulfill in order to recover Navier-Stokes, and you basically compute the eigenvectors, the A, I, K, blah, 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 and you choose basically the eigenvalues in such a way. Now, I have to tell you many things in a short time, but you will not be surprised to hear that leading non-zero eigenvalue control the viscosity of the fluid. And the viscosity was a problem because, as I said before, if you are in a lattice like this, there are very few collisions which are compatible with mass, momentum, and energy conservation, meaning that the particles do not collide much, meaning that they diffuse a lot, and high diffusivity means low Reynolds number. The Reynolds number is the velocity times the length divided the viscosity. The lattice gas has an enormous diffusivity. It could only simulate very low Reynolds number, no use. By the time you turn to the top-down, the very first omega there will give you an handle on the viscosity. So we could choose the viscosity instead of, and so we had the lattice-Boltzmann standalone, and that was the paper which really brought lattice-Boltzmann on. At that point, we were competitive with spectral, finite difference, etc., etc. So the top-down formulation was a second breakthrough, and was a matter of a few months later. Okay? So it all happened in a very short amount of time. And with that code, again, I mean, I don't want to go into detail, that would be obscure, but the carry-on, the take-home message is that with that we were competitive with respectable fluid dynamics. And then we started to do some application. I remember this. Flows in porous media is still one of the best applications of lattice-Boltzmann. This is a very primitive porous media, as you can see, but still this was 1989. And with Roberto, we were hoping, actually, that we could go actually to zero viscosity, which, of course, you cannot in any finite lattice. But just to say that since it was working so much on turbulence, what we tried to do was mostly turbulent flows. And here is, again, how nonlinear life is. A few years later, in 1992, a group at École Normale, they realized that as long as you deal with incompressible flows where the only parameter is the viscosity, there is really no reason to be working with a matrix. All you need is just one free parameter, and they published basically this is called lattice BGK because it comes from Batnagar-Gross-Crook, which did the same approximation in Boltzmann kinetic theory. And the big advantage is that you just have a one relaxation parameter instead of a full matrix. And this is still actually the most popular lattice Boltzmann in town, and they also gave actually the systematic expression of the local equilibrium, which is fully general. C sub I are the discrete velocity in the lattice. Rho and U are self-consistently computed out of the population. And so with this formula, you have the algorithm is ready for you. And that's why this paper is one of the most cited. By now, I think it has 3,000–4,000 citations. And much to my shame, I remember that Massimo Vergassola, some of you may know him, who was a very brilliant student in those days, always told us, but why don't we still using the matrix? And I said, who cares? Well, actually, we lost a big opportunity because we could have very well done this job. It was just next door. Just to see that, to show you that sometimes there are kind of obvious things and you don't do it because they look basically trivial. And so never underestimate. If something is simple, doesn't mean that you shouldn't pursue it, because sometimes that's exactly where you get the best payoff. Anyway, so this is, and then came another point. The point was that, again, I have to make a long story short, but there is a big crime that we committed when doing the top-down approach. Because we did not simulate collision. We postulated the existence of a local equilibrium, okay? But by the time you do that, you lose, in the local equilibrium you can encode mass, momentum, and energy conservation, but you say nothing about the second principle. There is no guarantee whatsoever that this will be stable. And the reason why it worked was a sort of lucky strike, because we didn't realize that finally this scheme does have an H theorem, like in Boltzmann kinetic theory, but we didn't think of it at all. It was only 1996, Ilya was visiting here at TIAC, and the reason why I put up Daniela's picture, because basically in those days she came with a nice suggestion on how to do crystal growth, which was a very successful application. Still, the paper is still going pretty well. So all I'm saying is that the lucky strike was that we had an H theorem without realizing it. And proving that the lattice BGK has an H theorem is not trivial. This is mostly Carlin, and Carlin then made a career out of the so-called entropic lattice Boltzmann method, because the entropic lattice Boltzmann method is much more stable. Okay? If I don't have the slide here, but let me just tell, oh no, I do have it the slide. The reason, I mean, it's simple enough for me to explain very quickly. You see the point. If I start with F positive and F equilibrium positive, as long as omega is between 0 and 1, I'm sure that this guy will be positive as well. But in order for running very low viscosities as needed for turbulent flows, I tell you without proof, but it wouldn't be difficult, you have to put omega 2 minus epsilon. You have to work very much in the over-relaxation regime, where you have no guarantee that starting from positive F and positive F equilibrium would return a positive. And we were consistently working in the unprotected region, and it worked. In fact, it worked up to a point. I remember that it worked up to omega 1.89, I still remember, which I used to call the Benzi constant, because we didn't know why beyond this value the code would crash, but later we understood, because then at some point you crashed the H theorem. But we were not supposed to work in this regime. We were supposed to work between 0 and 1, where the Reynolds number would have been miserable. So again, lucky strike that there was an H theorem. And ever since, well, of course, is that be perfect? Not at all. There are many issues. I would say still, if you want to do a body fit geometry, I don't think lattice, you can do it, but I mean, then you lose the basic power of the method. It's still comparatively difficult to do compressible calculation with strong heat release, et cetera, but by and large, the method is very powerful. And so this is, I think, the nice story, which I think would please Beltrami, because we started in 1986. These were the kind of flows that you got from lattice gas stereo automata. Very exciting from the computational point of view. Feynman was fascinated by the fact that you saw structure there, but the CFD people would laugh at you, right? I mean, what kind of... Then, in just a matter of a couple of years, we got something reasonable, but still, I mean, we were competing, but we are not superior to CFD. And all the way to the 20s, this is a landing aircraft. This is real engineering. This is a commercial code, and I think I have to credit Stephen Horsack, whom some of you certainly know, who unfortunately passed away far too early. And he was a strong advocate of the method. How to do turbulence bonding with lattice Boltzmann, that would be a thick topic. But I mean, this shows you a very nice trajectory where, in fact, statistical physics, applied math, high-performance computing all came together to generate what I would call an engineering tool, because that's what it is. And ever since, there are so many applications across scale of motion, racing cars, hemodynamics, foams, et cetera, et cetera. And I would say that if I have to come to closer to what we use lattice Boltzmann today for, Leo Kadanoff, again, a very prominent statistical physicist, was very interested in the early 80s. He thought that lattice Boltzmann, lattice gas, not lattice Boltzmann, would have been a simple model for complex flows. But as a matter of fact, no. I mean, you cannot use, you have to add some complexity to your scheme in order to do simulation like this, simulation where you have a flow with a lot of interface. And here there are two major developments. One is due to Tony Ladd. He developed lattice Boltzmann with fluctuation to address nanoflows and to address how to move actually rigid particles into the lattice Boltzmann flow. And this is today one of the mainstream of lattice Boltzmann. The second mainstream is how to insert potential energy, non-ideal fluids. Shan Chen is, I think, by now probably the most cited paper. It's very simple. You just add an interaction between, there are many smart ideas behind this simple expression, but essentially they could show that you can introduce an effective force between the lattice side at a given lattice side and the nearest neighbor. Is a sort of minimal potential energy model. And with this minimal potential energy model, you can generate interfaces. And the interfaces pop out of their own. That's a major advantage. You don't need to track, which would be a nightmare. Imagine a tracking algorithm for a flow like this, where there is much more, the surface to volume ratio is extremely high. That would be a total nightmare. When you run the simulation, the interface just pops out for you, provided you code up the interaction. But the interaction is still nearest neighbor, like this, you see? So with an extra 20 lines of code, you move to single-phase flows to multi-phase flows like this, which is a major practical advantage. And those of you who have coded lattice Boltzmann know that you can do multi-phase codes with an extra routine with 20 lines of code. So that was a time where people would still claim, and I would say, Roberto, it was mostly the applied mathematics community, they were claiming that we were doing uncontrolled approximations, okay? Which was not true, because we were doing approximation, but they were not out of control. So the statement was, and it was a diktat in PRL, there was a paper by a Chinese mathematician, which I will not mention, says you should never, because you cannot use lattice Boltzmann other than for Navier-Stokes fluids. But there is a rural region, in fact, especially in soft matter, where you are too small for the continuum treatment and you are too large for molecular dynamics. And I would say that as of today, soft matter is the region where, in fact, you have most of these cases. And the soft matter has turned out to be a gold mine for mesoscale techniques like lattice Boltzmann, which are in between continuum and atomistic. And I have to say that, Roberto, you tell me if I'm wrong, but kinetic theory was still perceived up to some 20 years ago as a corner where you do rarefied gas dynamics, where you use the real Boltzmann equation, and nobody really suspected that you can use it where, in fact, the continuum assumption is shaky, but still molecular dynamics will be an overkill. And that's exactly where lattice Boltzmann should be used for. And that's exactly where the long-lasting contribution, in my view, is. This no-fly region, And even in the books, you know, again, kinetic theory is mostly presented for rarefied. Now it's changing, okay? But mostly presented as a tool for rarefied gas dynamics. I think the most important contribution of lattice Boltzmann is to show that no, you can use it as a very effective tool to cover this no-fly region between the atomistic and the continuum. Of course, you have to do it very carefully, because it is true that you don't have any backup theory. Those of you who know kinetic theory, you know Chapman-Anscombe method, etc., where you show that you converge to Navier-Stokes. I am not aware of any result which would show that you converge to the proper macroscopic equation when you have this kind of interfaces, etc. Sometimes the equations are not even known. So it is true that you have to be cautious, but nevertheless, it is also true that if you have full analytical backup, where is the fun? Right? If you already know the solution, what's the point of using the tool? So it is true that you have to be careful and very, very critical of what you get out of your computer, but it's also true that you have a beautiful instrument to ask questions in very complex endeavors, where in fact a continued discretization would be much more unwieldy and most likely much less efficient. So unfortunately, I have to put up Massimo, who is nasty, as you know, but we must admit, I'm very sorry, I have to admit publicly, he's very good. And with Massimo and Simone, we had a great time in connection with Tim Kersir in Harvard, and this is really their credit. We using actually the technology in a broad sense of moving object into flows, into lattice Boltzmann flows. There has been a beautiful story for which I should take really no credit. We did first biopolymer translocation, blood flow simulation with finite size particles. This is a really complicated application. And later on, Simone, I think, did also protein crowding. I still remember this paper. I think this was one of the most impressive large-scale applications. They made it to the Gordon Bell final. I think Massimo holds the world record for the Gordon Bell finals. But Gordon Bell is the most important supercomputing contest worldwide. I think it's still running. But unfortunately, just to get it, I'm afraid it's not only a matter of science. But nevertheless, just to say that, I mean, we are talking 2013, 10 years ago, more than 10 years, and we were already talking petaflops on realistic geometries. This was real human arteries. And Simone remembers very well all the discussion with the Brigham School. I think Simone was there. Andato. Okay, too bad. I mean, this was really very complex simulation and really high performance. Actually, we extrapolated that if the code was called Murphy could have been extrapolated, it would have reached the exascale line in 2015. That didn't happen for many reasons, including the fact that, I mean, maintaining and developing this kind of complex software it's really very demanding enterprise. But just to say that there was really a very significant activity in the HPC side of the story. And along more or less the same line, much more recently, Giorgio, who was in fact a postdoc from Renzo Piva many, many years ago, he maintains a code, high-performance lattice Boltzmann code, and just in 2021 we did this calculation of the flow inside a sponge, which lives at minus 500 meters in the deep sea. And the question is, how does the sponge manage to survive? And in performing this, this is a 5 billion grid points simulation, so it's a large-scale simulation. We actually had reason to believe that due to the synergy between the structure of the sponge, which is really amazing, okay, if you look into this structure, it really looks like there is a lot of hierarchical design. There is a sort of synergy by which the sponge is able somehow to trap the water inside, and this in principle helps both feeding, food, so survival, and also sexual reproduction, because the sponge is an animal. So a marine biologist in the team suggested that fluid and structure as a sort of synergetic cooperation to facilitate life in the abyss. And I think this was the only reason why we could make it to nature with pure simulation, which is a rather rare event. And here I credit Giacomo cannot come. He just called me that he has a family. But I think Giacomo and Giorgio deserve the credit for this HPC performance. And then, okay, how much time do I have, Roberto? I think I can be very quick. Then we discover how to, make things a little. This is a typical lattice you would use for fluids. This is not a cartoon. That's what you do. You have 18 discrete speeds. And one thing which, the most important thing I forgot to tell you, actually, I take the opportunity now. If I had to say what is the secret of lattice Boltzmann in one word, the secret is here. In Navier-Stokes you have U grad U, right? Meaning that you move the momentum along a trajectory which is curved, because the trajectory is given by the velocity itself. Okay? So if U is a complex field, fluctuating, turbulent, deformed, etc., you have to move information, or you have to ride a very wild horse. In lattice Boltzmann, you never have to do that, because you work in 6 dimensions. X, Y, Z, and 3 coordinates for the velocity. In the early days, I forgot this to tell you in the beginning, for at least 5 years, each time you went to a conference presenting lattice Boltzmann, they say, are you really solving Navier-Stokes? You must be mad, crazy, because we have a problem in 3 plus 1D, 3 space dimension plus time, and you go to kinetic theory where you have 6 dimensions. You must be, this is totally stupid. The reason why it is not stupid is because, remember the streaming. The streaming means that if I have a right moving particle, like in the cellular automata, here there is full continuity with lattice gas, I'm blind, I'm not thinking. When the clock comes, I move right. And if I'm a front mover, I do that. And this information transfer always goes that way, along straight lines. And you always land on another lattice site. So the information always moves along straight lines, regardless of the complexity of the macroscopic field. This is a major advantage. And this, like in the lattice gas, is still an exact operation because it's a memory shift, no floating point. So the transport part in kinetic theory, in the lattice kinetic theory, is exact, computer-wise. As opposed to U grad U, where you have floating point operation too. So I think this is still something that lattice Boltzmann has inherited from the lattice gas picture. And I think is the major strength of the method. And it would not be possible unless you go to higher dimensions. So it's yet another instance where higher dimensions look like a nightmare, but in fact they provide you an advantage. Okay? So we use these lattice, high-order lattices for many applications, and here I think the most recent time, this is a picture I really like very much, not because of the science we did with it, which is nevertheless interesting, because out of this project we got the ERC in 2017, but we got another 2 ERCs, the small one, proof of concept, and lately, starting this month, a Pathfinder, which is the industrial version of the ERC. But, and okay, that would be many talks on its own, how to design materials out of microfluidics based on droplets. When we started, this looked like a simple thing to do, but no lattice Boltzmann would have been able to do this because the droplets would have merged. So I think Andrea Montessori was mostly responsible, but the entire team for the lattice Boltzmann, which prevents merging. But the reason why I like this picture is because, well, Fabio Bonacorso, you don't know, is a Tor Vergata. Pino, you know, but Andrea, Marco, and Adriano. Andrea got an associate professor straight from postdoc position in Roma 3. Marco is a primo ricercatore here, and so is Adriano. So during the UDRC, and I'm very happy to acknowledge the cooperation with Roberto and also with Emilio Campana, we had the chance to get, oh, thank you. Go ahead. We had the chance to generate permanent positions, and I think that was, well, I think that was a good use of the ERC money. And now we still cooperate, less tightly, of course, but this to me, this was a very, very rewarding experience. And we are still actually running, the Marco and Adriano ran this, the second POC, and Mir, which is a student at a postdoc at IIT, will help me with the Pathfinder. So just to say that this is still an outcome of the lattice Boltzmann for complex flows, okay? In a very generalized sense, but follows along that line. I don't think I should talk about relativistic, but let me spend just a few final words about what keeps me busy mostly in firsthand these days, you know, of the PNRR, and quantum computing. So at some point IIT asked me, well, why don't you take a look at quantum computing within the PNRR? I said, yes, why not? And we decided to do something rather weird, which is trying to do fluid dynamics with quantum computing. Now, that would be another talk, but you know that quantum computing usually has been invoked by Feynman to do quantum problems. Famous statement, nature is not classical. If you want to simulate nature, you should use quantum computers. But Feynman was mostly referring, this is a quadrant. In the horizontal line, you have CC means classical computer for classical physics. CQ means classical computer for quantum physics. And that's how we do simulations as we speak. I mean, this is 99.9% of the simulation work. The quantum computing usually is the quantum computing that Feynman invoked was basically this. CQ is the many-body Schrödinger equation, which is almost a mission impossible because it's a problem which lives in hundreds of thousands dimensions, and you cannot solve a problem with so many dimensions with grid methods, and even Monte Carlo has its fair share of trouble. So Feynman says, don't solve the many-body Schrödinger equation on an electronic computer, develop a quantum algorithm. And this, as we all know, has its fair share of problems. But what we are trying to do is even worse. We are trying to use quantum computer for classical problems, and not just classical, but like Navier-Stokes, where they are nonlinear and dissipative. And you know that quantum mechanics, quantum computing is rooted into the fact that quantum mechanics is linear and unitary. So in these days, I'm struggling with, and wherever we're struggling with how to code a nonlinear and non-unitary problem into quantum computing, it's a lot of fun, but it's also very frustrating because you find a wall, you turn around the wall, and there is another wall. That is very technical, but let me tell you, there is a technique, you might have heard, Karleman embedding. Have you heard? It basically transforms any finite dimensional nonlinear problem into an infinite dimensional linear one. So we said, okay, at least let's turn around nonlinearity. And when we ran the lattice Boltzmann with Karleman, it is excellent. Navier-Stokes would be a nightmare. Lattice Boltzmann is pretty good at Karleman linearization on classical computer. But when you try to move to the quantum, which is the real story, you meet with I don't want to be technical, but all sorts of complexity. And so far, it's just like a slalom. We have a circuit which is very deep, so you will be killed by the quantum noise. We find a way of reducing the circuit depth, but then it turns out that the calculation becomes probabilistic, and the probability of success is miserable. Then you want to enhance the probability of success. There is a series of algorithms called amplitude amplification. I'll just give the names, it's very technical. And they enhance the success probability, but only if your matrix is unitary. So now we are trying to turn around and generate an amplitude amplification algorithm for non-unitary updates. And honestly, I don't know whether we will ever succeed. But it's a very rewarding exercise from the intellectual point of view. Whether we will ever end up with a viable quantum algorithm for fluids, honestly, I do not know. But it's fun. So this was a long ride, covering 3 decades and a half. There is still a lot to think to do. But I mean, one obvious thing to do is to enhance the lattice Boltzmann that we are using today with machine learning models to do even more complex flows. Kinetic models of fluid turbulence is very technical, I didn't mention, but there is a lot of work to be done to improve this, the codes which are used in the commercial version of lattice Boltzmann. In the nanofluidics, we do not know how to treat strong fluctuation. Just to say that there are still many items where, even though the topic is very mature, there is still a significant amount of work to be performed. So I think I'm almost over with my time, so it's thanks time. And this is an articulated thanks. And don't look at that because I'm sure I forgot some name, okay? But just to mention that, as I said, this is certainly not a one-man show, and during the years, and I really mean it, I have been profiting of the collaboration with so many bright people who have taught me much more than I could even imagine, and I think Rome has been instrumental in this respect. It's a fatiguing city, as we all know, but at least you can always find good people, very good people. I could have not done that in any other place, I think. And of course, I have to thank the committee, my nominators, Michele Benzis, you might not know, Giorgio Parisi, you'll know, Roberto, of course, and also because during my more than 20-year stay in IAC, I could enjoy really a lot of, that's basically the bulk of my career. So I'm very grateful that I could develop my scientific career here at IAC. And of course, George is not here, but I owe him some special thanks. First of all, the fact that he, to me, it's still unusual that you have as a laudatio the letter by George, which is kind of embarrassing, but I'm very, very pleased. And I have to say, George is not here, but maybe doesn't change anything. He has been really constantly supporting and very friendly to me. I'm really grateful to him. And not only to me, I think George is really very important for all our community in general, meaning statistical physics, high-performance computing, and applied math. I think he is really playing a very major role in giving dignity and dignifying this community. So I'm sorry he's not here, but I'm very grateful nonetheless. And of course, as I used to say, lately, thanks to Ludwig, because it's like the espresso, no Boltzmann, no lattice Boltzmann. So he really did it. And I'm sure that if he had a computer, he would have invented lattice Boltzmann in no time, because if you look into his horrible book, I mean, horrible says super thick, The Kinetic Theory of Gases, he writes explicitly in a discrete velocity version, and he says, this has probably even more physical meaning. So it was there, no question. Okay? Maybe he would have not thought of fluids, but I'm pretty sure that Boltzmann with the computer would have invented lattice Boltzmann overnight. And of course, that's been a long ride over several institutions, and of course I'm grateful to them all, and particularly Italian Institute of Technology, that's where I am for a few years, and of course the CNR, where I spent basically the bulk of the story, which I've just been telling you. Thank you for your attention.